Thank you very much for the opportunity, and I very much appreciate this. So I'm going to talk a little bit about machine learning and AI. And by the way, if I don't start speaking about contents which are not on the slide, I'm trying to trust someone to be awake enough to alert me. But that should be the content slide now, is it? Yeah. So I'm going to talk a little bit about AI and machine learning and what do we mean, and I'm going to talk about some healthcare applications in general. And then I'm going to talk about two applications that I think are very exciting in the context of AI. One is screening for undiagnosed patients, and the second is around modeling disease progression. And then I'm going to wrap up a little bit by speaking around some of the bigger challenges, that, as I see it at least, with widespread implementation and adoption of some of these ideas and some of these methods. I guess I should get the apologies in first. I feel slightly fraudulent here in terms of I certainly do not have a medical background and actually work very little in the UK, and including in primary care, and also not from a technology background. So that's just a few of the apologies. However, hopefully what I'm about to tell you are some potentially very exciting applications using machine learning. Most of the work that we currently do is sponsored by pharma, so there's a very pharma commercial lens to a lot of this. But as hopefully you'll see as we go along, and then hopefully at the end as I wrap up, this will be very inspirational in terms of some of the potential applications that we can start to think about in terms of integrating with healthcare providers. So what do we mean by AI and so on? So John McCarthy, back in 1956, famously described AI as machines which can perform tasks characteristic of human intelligence. And one thing worth noting about that is that that was back in 1956, which is, you know, a pretty long time ago, given a lot of the hype that's currently around AI. The second thing is it's a very general definition. So there are two things here to note. It's a very general concept, and it has been around for a while. But perhaps somewhat confusingly, more and more these days, especially the last 5, 6, 7 years, when we talk about AI, really we're actually talking about a subclass of machine learning called artificial neural networks, and its application to things such as Siri and driverless cars. I'm going to talk more about this in a second. But it is entirely understandable that anyone outside of the sector is utterly bewildered, since there are generally two notions and definitions of AI kicking around: a general one that's been around for a long time, and something that's quite specific. So you're all entitled to be entirely confused. So I've mentioned machine learning. I'm going to try to elaborate a little bit on what I mean by this. So we might do a study very traditionally and very typically where we want to look, for instance, at the association between, let's say, a risk factor and an outcome. So it could be, for instance, you know, what is the association between, let's say, age and BMI? On the one hand, as risk factors, and you know, the risk of diabetes, so diabetes being the output. So, you know, we would go away, we'd look at electronic medical records or whatever the relevant data is, and we would look at the association. Because you've got two risk factors here which are correlated, then we may use something like a logistic regression, which I'm guessing most people are familiar with, a simple regression that controls for that correlation between these two risk factors to produce an independent estimate of the association between each of these risk factors and the outcome. So this is a really standard way of doing things. And, you know, it's the right way, and we've been doing this now for, I don't know, 40 years, and we'll probably carry on doing it at least for the next 40 years and probably the 40 years after that. The point here is, this is a question or a study where the primary objective is inference, so we're looking at associations, and where the variables of interest are predetermined. The study type that I've mentioned here is perfect for this. But if instead I asked you the question, not what is the association between these two risk factors and diabetes, but tell me which patients are most likely to get diabetes? That's a different question. And it's a question where the primary focus is on maximizing predictive accuracy as opposed to inference per se. And it turns out that if you want to do a very good job at building the most accurate algorithm, you need to use as much information as possible. You need to use all of the data that you have available. So you cast the net very wide, and you're looking at your database, and typically, you'll use hundreds, if not thousands, of variables. And this is what machine learning is. It's an empirically driven, as opposed to hypothesis-driven approach. And the primary objective is maximizing predictive accuracy. So I mentioned here the point about using lots of variables. So this is critical. And in order to, machine learning is what we call a flexible non-parametric method. But what that essentially means is it's very, very good at picking up complex associations in the data. And that's why it does very well. The problem is that a priori, we don't know which data is complex and which isn't. And there's a rough rule of thumb that we generally use, which is to say the more data that we have available, per patient in particular, so the higher the dimensionality of the data, then the more complexity we can expect to find in the data. And by complexity here specifically, we're talking about generally two things. One is nonlinear associations, which is familiar to everybody, but the other one is what we call non-additive or interaction terms. So it's things that when happen together are deterministic of the outcome in question. And just to try and really illustrate this point about the merit or the value of machine learning being very linked to the dimensionality and hence the complexity of the data, there's a few examples on this slide. So one project that we did, for instance, was to try and predict the onset of labor for pregnant women. This is following a particular treatment. And we used the old-fashioned approach using a logistic regression, and we used the machine learning approach. And the old-fashioned approach had a precision of 77%. So of every 100 patients flagged, 77 were accurately, of every 100 patients flagged who should have labour in the next 24 hours, then 77% of them did. Actually, the machine learning did slightly worse, about 74%. And I wanted to illustrate and to draw this to your attention. The challenge here is that we only had 20 variables available from this clinical study, and they were generally binary variables. The point is, this is by no means machine learning helped us improve the situation. Moving on to, that's what I call a low dimensional, sort of low to medium dimensional data set. This is an example project where we were predicting medication non-adherence, so which patients were likely to non-adhere. This is on statins. And we had 60% with the old-fashioned route, and then with machine learning, we had a precision of 64%. This is an improvement. There's about 50 variables here. It's about an improvement. But this is, no one's really going to get excited and write home about this. But moving more to medium and high dimensional data sets, we can begin to see some real transformation of results. For example, we did a project to predict which patients currently who had hepatitis C who were undiagnosed. Precision of sort of 2% for the old-fashioned method, and then actually 87 in the original version and 97 by the end with the machine learning method. So that is an absolute transformation of result. This is dramatic. Now, we don't always get quite that stark result, but again and again and again, where you allow a method to exploit the full data that is available, then you can begin to see very, very substantial uplifts in model performance using machine learning. So it's not always relevant, it's not always helpful, but where you have medium or high dimensional data, this can lead to some very important results. And if you're trying to find needle in a haystack, such as patients with rare diseases, you absolutely need to have a very high precision model. So there's other examples here, and I'm going to touch on these later on in the talk, but that's the key message here about when to use machine learning. Just a comment on, as I alluded to earlier on, there's a sort of growing sort of excitement around machine learning in recent years. And for me, I think I would say there are three phenomena that are helping fueling this, this increase. Firstly is the availability of data. So we all know that there's reimbursement data becoming more available, there's EMRs, there's lab data, there's lots of other types of data, social media and so on. It's not only the volume of each data, but they're increasingly being linked together. And what this means is that per patient, you generally have a lot more information than you used to have. So here we have generally more and more high-dimensional situations, and hence more opportunity where there is the potential for value from some of these machine learning methods. Second is around technology. It used to be the case, not very long ago, when the challenge was, we've got all this data that's emerging, but there's only a certain amount that I can fit on my floppy disk. Long gone are the challenges around storage, where storage was the primary bottleneck. When we solved that problem, then there were people like me that said, this is great, we got this data, but I want to use machine learning, and we just don't have the compute power. But now, increasingly we do. There's things like TensorFlow that uses a lot of GPU. We have Hadoop and Spark. Systems like this that enable the rapid retrieval, parallel processing of a lot of jobs to do a lot of these heavy compute tasks simultaneously. There's a way to go, but with huge step forward. And then for me, the third phenomena that's driving this change is around the methods. So when I did my PhD back in the 1990s, if anyone then was studying neural networks, they were considered to be a bit of a dinosaur, simply because in the decades that had gone before, we had made very, very, very little progress in this field. But the main reason we've made a little progress, in part at least, was around the compute power. But as soon as that became available, we started to use these methods to really make big strides forwards. This is just one example, neural networks. So, we've talked about, I've mentioned the driverless cars and Siri. There's lots of applications that at their heart use a lot of these neural networks. In these very complex challenges, these are a set of great methods, and there's been huge investment of R&D in this space. So the coming together of these three factors, in my view at least, are a lot of the reason why we're seeing increased applications. And thinking about each of these phenomena, they're going to increase yet further. So I think we're just at the beginning, really. One application that I wanted to draw to your attention, and this, I always find myself sort of on this tightrope between being an enthusiast and an evangelist around machine learning on the one hand, and at the end of the day, that puts a roof above my head and bread on the table. But at the other time, trying to be a realist and trying not to get too excited and trying to control expectations. And so I sort of oscillate violently between a wild optimist on the one hand and some kind of doom-glooming monger on the other hand. And in a way, this is an example that illustrates this, because this is it's actually a paper that came out in August by Nature. It was published in Nature Medicine. It was a collaboration between Moorfields and Google DeepMind. And what they did is look at a lot of OCT images, 15,000 of them that they had at Moorfields, and what they did was try to predict the urgency of referrals. And they did a great job. So the results were approximately the same as a clinical expert, which is fantastic. Now you can imagine that if this was implemented, then we could really help for example, the triaging process, which would be a wonderful application. And if you read this literature, then there's a lot of examples here around images being used for diagnostic processes, especially in cancer, different tumor types. Increasingly neurology, Alzheimer's and MS are just two areas. And in general, there are some wonderful, wonderful papers showing some fabulous improvements in accuracy in recent years, comparable in many ways and sometimes better than clinical experts. The problem is, if I walk into my GP or to my specialist. There are no such tools that are being used. Certainly 99.99 recurring % of instances. And the question is why? And I think there are a lot of reasons why. But here are some of the reasons. So it turns out that these image recognition software solutions driven by AI, it turns out they're not very generalizable as a rule. So if you take them and try to apply the algorithm on a different device, often they don't work. Often, in fact, they don't work even if it's the same device but a different operator. And sometimes they don't even work if it's the same device, the same operator, but different operating settings. And I've not even mentioned being applied to a different population. So we often need to train these algorithms, retrain them. But the problem is they're very, very data hungry. So the generalizability is a huge problem. And where the community is right now is trying to say, how do we make this more generalizable? And how can we come up with results that are just as good as this, but use a lot lower volume of images? So that's where the field is at the minute. I think given the progress that we've made, I think we are absolutely going to carry on seeing great leaps forward. But we're not there yet, in my view. Certainly not in terms of widespread application and adoption. So I want to talk about some of the applications that we specifically are involved in. This is in my team. So I note that we do virtually all of our work sponsored by pharma. So a lot of these are commercial applications. But as we go along, hopefully you'll see some of the applications to integration in health system settings. So one of the things we do, and I want to dwell on this in a little bit, is develop algorithms that can identify undiagnosed patients. It's a big area. Second is around modeling disease progression. If you can identify patients who are likely to experience rapid disease progression, then we can think about tailoring more appropriate, arguably more aggressive, earlier intervention for these patients. Non-adherence is another big topic. We know that non-adherence is a huge problem. We know that a lot of people don't adhere to their medication. We know that that's linked to really bad outcomes often. Can we do something about it? Either retrospectively for those who we observe as non-adherent, or maybe those that we can predict and be proactive there. And then the final area is around predicting treatment response. So this touches on the agenda around precision medicine, which I'm going to circle back to at the very end. So I just want to talk now about identifying undiagnosed patients. I'm hoping that I'm clicking correctly. Is that the overview? Yep. Yeah. People are still awake. That's excellent. I generally, if the roll of the noise of snoring is not too loud by the time we get to the end, I consider that a magnificent success. Okay, so we all know that underdiagnosis is a really big problem. By underdiagnosis, I mean people who never get diagnosed or people who get diagnosed late. So in rare diseases, we know it's a huge problem. On average, it takes nearly 5 years between the average onset of presentation of symptoms and a correct diagnosis. I mean, in cancer, it's often the case. Lung cancer, I mean, I'm sure most people would know far better than me in this room. But in lung cancer, at the point at which most people are diagnosed, it's often too late for a very meaningful intervention. And the sort of quote-unquote tragedy about this, from a data science point of view, is a lot of those people are leaving footprints, digital footprints, and we can do something about it. There's a lot of evidence now that says you can leverage all of that data, you can build algorithms, you can predict, you can bring forward the potential point of diagnosis by using these algorithms by a few months in many instances, and hence make a transformation in the life expectancy of those particular patients. We do most of our work, and it's not just true of us, but in generally where the industry is at the minute, using what we call US commercial data assets. So it turns out in the US we have, for people who don't know, they're sitting too well, but we have, fabulous data. It's on 200+ million patients. This is from reimbursement data from claims. We link that with prescription data. This comes in, virtually daily. It's a huge data lake that we've got. The latency is low, the coverage is high. We can use this for both medical scientific and also commercial applications. Obviously, the patients are anonymous, but with some arguably very liberal restrictions, the physician IDs are known and can be used. And these are used by pharma companies for a range of disease awareness initiatives, and also by, by their sales teams to send sales reps. Where the industry is heading, and where we're very excited, is to start pivoting some of these ideas, technologies and algorithms and collaborating with health systems to insert these into the clinical workflow. So here's an example which is actually we did in the UK. This is a few years ago now, but in many ways this sort of set our train of thought off. And hang on a second, this is a rare disease. So this is just some more numbers here to illustrate the point around rare diseases in particular and the late diagnosis. So on average, people see, over 7 physicians, it takes nearly 5 years. 40% of people are initially misdiagnosed. And I can't emphasize this enough, that certainly in rare diseases, a lot of patients are taking a long time before correct diagnosis, and from a data science point of view, they are leaving this digital footprint which we can use, and we have used many times now, probably 30, 40, different rare diseases for which we've developed some very good algorithms for. So this is a case study, a rare disease based. This is actually a project that we did in the UK. This is a disease called tuberous sclerosis complex, TSC. Prevalence is around 1 in 15,000, and we linked, this is CPRD and HES data, so primary care and secondary care data. And this is a sort of great study for us, because it justified my sort of begging bowl to my investors, or my senior bosses with their budgets, because I said this thing works, so let's invest in it. So what we did actually, we talked to a lot of experts in the field, and we said, well, if you were looking for these undiagnosed patients with TSC, what would you look for? And they came up with a whole bunch of stuff, and then we sort of, we built a little scorecard, and we tried to find some of these patients. And for every 100 patients that were flagged by this, the rules that we had learned from these clinicians, for every one patient that was found who was subsequently diagnosed with TSC, around 25 didn't have it. So roughly it's a screening rate of around 1 in 25. So, I've got to say, these clinicians were not terribly delighted by this. And they said, well, to be any use for a screening algorithm, it needs to be at best 1 in 10 and maybe 1 in 5, if not better. Clearly 1 in 25 is better than 1 in 15,000, which is what the prevalence is. But it's not really at the stage where it's operationally viable. So then we said, okay, well, we've learned a lot from these clinicians. I mean, it's, this is clearly somewhat better than random. These guys clearly know something. So then we used various statistical methods to use the information that they provided, but allow a model to determine the weights. And we improved. We went to 1 in 13. So, the stats guys in our team were happy. The clinicians were a bit disgruntled. But then, then we introduced the machine learning guys and said, well, can you do any better? And at this stage, they had no domain knowledge. They knew nothing about the disease. And so they went away, and we pulled every single raw code from this data, so it's 100K worth of bits of information. And they ended up with a screening rate, and by the way, this is all tested in blinded external data, of 1 in 6. So they were very happy. And then they went back to the clinicians in a very humble way, and they said, well, maybe the best solution is some hybrid. How can we better incorporate your clinical knowledge into our machine learning method? And we did this in various ways, feature engineering. We used a bit of a Bayesian framework, lots of bits and pieces. The point is that we then had a screening algorithm of 1 in 4 success rate. This is now good enough to be used. Everyone was very excited by the end. And I think there's a few lessons here. This is, to me, one example of how machine learning can really, really help us. The problem with undiagnosed conditions often is we don't know what these things we're looking for, symptoms, other conditions. we don't know the temporal associations, and we don't know the weights that we need to assign to these. So machine learning is an appropriate set of tools that we can use here. And the other thing is that the best solutions, and we've done this many, many, many times now, that in every single instance, the best solution is some combination between machine learning and incorporating that clinical or someone say it for me.
Epidemiological.
Yeah, the epi knowledge. It's not even started on the gin and tonics. And then I just wanted to come back to this hepatitis C instance. Again, I'll not dwell on this, but this is where we wanted to identify some undiagnosed patients with hepatitis C. We did a great job here. This is 150 million patients in the US that we used for this. And then we provided a list to our client who's now very actively used this list of doctors. So we predict patients likely to have the disease but are undiagnosed. We link them to the treating physicians, and then and that's the list that we provide, and that's being used for a variety of disease awareness campaigns and direct sort of outreach activities. They find it very, very valuable. I hope some of the physicians do, but that's a different question. Okay, so this is the contents. So I want to now talk a little bit about modeling disease progression. So again, this is a really difficult thing, especially very complex conditions. Heterogeneity, there's a lot of complications. It's not very difficult to understand which patients at any point in time are most likely to experience increased disease activity or progression. So this is an example in a particular area in neurology, and what we did here was we partnered with a group of neurologists. We pulled their EMR, and then we built some models. And we did a great job whereby then we bucketed everyone according to their risk of disease progression. And then we grouped everyone into deciles there, and people in the highest risk decile were 7 times more likely to experience subsequent disease progression than patients in the lowest decile. Again, this was all validated on external data. That sort of information is really, really helpful in a situation where, when we sat down with a lot of clinicians in this to begin with, we said, oh, how well do you think it is possible to predict? And they said, oh, maybe some people are obvious, but no, most people are not, and I'm very, very skeptical. So there was great skepticism. They were very surprised with the results, and when we showed them and what sort of attributes, they were, yeah, that makes sense. So that's just one example. Thinking on to the more commercial, so we're developing a web app for that, which should be launched fairly soon. Twisting this for 1 second again, to the commercial applications, because we can learn a lot from this. What pharma companies often have a challenge with is, someone gets diagnosed, maybe there's a bit of a delay, and then there's a treatment choice, and they want to be present prior to that treatment decision to influence the choice. But it's extremely difficult to know when the timing of that intervention should be correct. There's a lot of, people generally have used business rules. Again, I'm talking about the US when we have the data, but they've not been very accurate. Using machine learning, we really can do a good job of predicting these upcoming therapy transitions and getting the timing a lot better. It's very correlated to disease progression, of course, generally speaking, understanding upcoming switches in line of therapy. So this is just an example of, in lung cancer, patients were on first-line treatment, and the client wanted to understand which patients are more likely to have rapid disease progression and hence be appropriate for second-line treatment, and this client had a product for second-line treatment. So the first thing we did actually was, we said, well, have you got some rules that you intend to use? And they said, yeah, here's 15 new rules. And then we said, well, how good are they? So we need to benchmark. And they said, well, I have no idea how good they are. We think they're quite good, but, So we said, well, let's test them. And then it turns out they had a 41% precision, which is amazing. Normally when we do this, the precision, if it's 5%, then we get very excited. And then we said, are you sure you want us to carry on? We're not in the business of turning away money, but are you sure you want to carry on with this project? And they said, okay, well, let's see what you can do with the machine learning. And then we did it. We got an increase to 89%. And then they said, oh, well, this is fabulous. This is a great improvement. The problem is, though, it's so complicated, your model, we couldn't possibly operationalize it. So then we said, well, we know you can handle 15 variables, so can we just identify the most important 15? So, we did something called recursive feature elimination. We identified the most important 15 variables, and that had a precision of 79%. So a lot better than their original. So that was another success, and we've done lots and lots of projects like this all the time. We provide alerts and physician lists. So that's just a couple of different examples. I want to sort of broaden the topic out now in a sense, because I think what I've hopefully persuaded you of is that here are two areas, which is identifying undiagnosed patients and hence accelerating time to diagnosis. And the second area is around modeling disease progression. And I think, in some instances, I think we're fairly clear on what the risk factors are for these things. You don't need some clever PhDs in AI to do this. But often we really don't know. And we really do need to turn to some pretty advanced methods to help us understand which patients are at risk. And I think that hopefully I've illustrated that the use of machine learning in these two areas can, in theory at least, really, really help and be a lot better than some of the traditional methods. Most of these applications, as I mentioned, are very commercial at the minute, used for pharma. But what we've started to do is think about, well, there's obviously great benefits for providers and for patients. So can we start to use these more and more? So, we're doing various, building partnerships, doing various pilots to do exactly this. So with one particular rare pulmonary condition in the UK, we've partnered with the leading centre there. We've developed an algorithm together. We've just submitted that paper for a publication. And we're just rolling out an actual pilot in their clinic. And if that's successful, we're beginning to talk to the relevant national bodies about, well, how do we do this on a nationwide basis? If that's successful, we've got other ideas. It would be wonderful to get to a point where, we can develop algorithms for a suite of different conditions, lots of different instances, and use these in some way or another. So it could be pop-ups in EMRs, but there are challenges with that. But in some way or another, either information direct to the practice managers that actually genuinely help support that clinical decision-making process. I think that AI absolutely has a role here. There's a lot of challenges before we get there. But for me, at least, a lot of the work that we've done for commercial clients, often in the US, for me, demonstrate some of the effectiveness of these methods. We have a long way to go. There's a lot of other stakeholder engagements, stakeholder management needed to do, and consortia, not just from the provider space, but also from EMR vendors. There are challenges around interoperability and so on, and the previous speaker to me, and no doubt others in this room are far more capable and able than I am to think about solving some of those challenges. There's a role here for pharma as well, but what is the right role? They can be a sponsor and a thought leader. That's part of the role, but these algorithms absolutely need to be developed with their clinical utility for the foremost. So the arrangement needs to be hands-off. In many instances, that will work, whether it's both private and public good, but not always the case. And for me, some of the low-hanging fruit are very much around screening algorithms for difficult to diagnose conditions, risk stratification for very complex and heterogeneous conditions. Less so is treatment response, and I'm going to elaborate on that. Have I got time for one more slide?
2 or 3 minutes?
Okay, I'll do one more slide and then I'll wrap up. So I want to talk about precision medicine. This is getting the right treatment to the right patient at the right time. In many ways, this is a holy grail, and I absolutely believe that AI has a key role to play. But I think we're a very, very long way from being successful. For starters, and we've done a few of these projects now, it turns out, I mean, what we're talking about here is identifying which patients are more likely to respond better to treatment A versus treatment B. This is, in epidemiology, what we call comparative treatment effect heterogeneity. This is really hard. It's really hard because any one patient at any one time never takes, the alternative treatment. So we always have to estimate a counterfactual, and it's difficult. So it turns out that a lot of the potential signals are only captured in very rich biological data or phenomics data. That's typically not integrated with a lot of the other data we have. So before we can have a real revolution in this space, for me at least, I think we need the widespread adoption and integration of some very rich biological data. There's a second whole class of problems around inappropriate methods, which were this to be a different audience, I'd love to talk about augmenting loss functions, but maybe I'll skip on to the next one, which is the regulatory front. So the things I've mentioned around screening tools and things like this, the regulatory hurdles are somewhat less onerous. And that's pivotal. Because at the minute, there's a slight juxtaposition between, on the one hand, AI algorithms to predict treatment response, which often need to be very frequently re-optimized in a deployed environment to take account of changes in data and prescribing behaviors and everything else. But on the other hand, the need to often validate these in an external environment, sometimes even a trial, which can be very burdensome, both in terms of time and cost. How do you reconcile both of those? There are solutions, people are talking about them, but we need to get better at this, certainly by the time that these algorithms are good enough to be widely adopted. So I'm going to stop there, but thank you very much indeed, and hopefully you've seen some semblance of relevance to the worlds in which you all inhabit.